Now, today's class is on shoulder biomechanics. I have a combined presentation on shoulder biomechanics and total shoulder replacement, but I would concentrate on shoulder biomechanics in this class. Okay, so I will be concentrating on the details of the shoulder joint, its movement, the muscles responsible for the joint, that means elbow, considering the shoulder joint, the elbow, the thorax together. Okay, so let me define the shoulder as it is constituted by four bones, as you can see here. That in the picture, there is humerus, there is scapula, there is clavicle, and the coracoid process. Okay, so these constitute the shoulder. So we have several joints. There are several joints that actually constitute together what is known as the shoulder joint. We start with the sternoclavicular joint. We start with the sternoclavicular joint. This is the laser pointer A. We have the acromioclavicular joint, B. We have the glenohumeral joint, the most important joint that gives rise to the motion of the shoulder joint, the glenohumeral joint, where the scapula and the humerus are articulating. And we have the scapulothoracic gliding plane. So the scapula, which is the shoulder blade, is gliding on the thoracic cage, and that is a connection between the scapular bone and the thoracic cage. So we call it scapulothoracic gliding plane. So the normal motions of the shoulder, please remember that the shoulder joint actually gives rise to maximum range of motion. So we have abduction and adduction, two opposite movements. Abduction is raising the arm, whereas adduction is lowering the arm. We have flexion, extension. There is also horizontal flexion extension. So flexion extension, as you might know, what is in case of the shoulder, you can see in many pictures available. You have horizontal flexion and extension. You can also have exorotation and endorotation. So rotation, inward rotation and outward rotation. The scapula is a very weird shaped bone. Okay, as you can see, this is the front view of the scapula. Okay, you can see that it consists of several solid bony ridges, and also it consists of thin laminated structures. Okay, very thin laminated structures. So from the front, it looks like that. Here it is glenoid. There is acromion here. Coracoid process is here. This is the shoulder blade, so as to say, which is very thin and laminated type of structure. And popularly, this is clinically known as fossa area. So you have supraspinatus fossa. Supra is top superior. So supraspinous fossa is fossa is on the top. Infraspinous fossa is towards down. So this is the fossa areas. From the back, you can see that clearly the scapular spine is visible, and the fossa area on which the number 2 is marked. You can see easily. So this is the fossa area from the back side. If you are trying to look from the side, it would look somewhat like that. So there is a glenoid cavity, okay, and you can see clearly how this scapular spine is curving out and forming the acromion. Another bone coming out of the scapula is the coracoid process, as I am indicating with the laser pointer. And there are ligaments and muscles all over the shoulder, which actually give rise to a large range of motions. Now, as I was telling you, there are about 20 muscles which crisscross the shoulder joint. And since it gives us the maximum range of motion, so there is contribution of different sets of muscles for different types of movement, as I had indicated earlier in the class. So we have the major muscles that contribute in the movement of the shoulder are indicated in the figure. This is actually drawn by me itself. Okay, this is pictures that actually were included in my PhD thesis long back, but I took the pain of generating these pictures myself with very limited resources, which were more than 20 years ago, 25 years ago almost. So there we had the primitive version of Word during that time, and I used the word, art to generate these sort of muscle attachment sites. So if you're looking from the front, you can see that there are large muscle attachments like muscle serratus anterior, and within bracket you can the number that is indicated within bracket is basically the lines of force that is represented that is used to represent the muscle action. Okay, so if the muscle is distributed over a sort of large area or over a line, so we have more number of lines of force representing the muscle action or line of action, because it would be erroneous to actually represent the different lines line of action of the muscle elements by a single line representing the muscle action. So the more the distribution of the muscle over an area, over an attachment site, the more is the number of lines of force. Okay, so with that, say 6 lines of force is adequate to represent the complex action of various important muscles having large attachment sites. So muscle serratus anterior, as you can see, is all along the medial border. So we call it, this is the medial side of the scapula. This is the lateral side of the scapula. So lateral side, we have the glenohumeral joint, which there is a reaction force, a very large reaction force of the glenohumeral joint. And the muscle serratus anterior is attached on the medial border, all through the medial border. In the front, we have large muscle, which is also represented by 6 lines of force, and that muscle is subscapularis in the front. Okay. You can also see that since we have, as I defined already, the shoulder joint which is constituted of several joints. So there are points on the scapula at the connection where the connections occurs between 2 bones. So the AC, the acromioclavicular joint reaction force, is marked here on the acromion. We have the glenohumeral joint reaction force because of articulation between the glenoid and the humerus. On the medial side and also more in the inferior side, we have actually 2 points which represents connection between the scapula and the thoracic cage. So to start with, we actually have the model. Finally, I will discuss a little later that the connection between the scapula and the thoracic cage is represented by 2 points. As you can see, the thorax TS, this area is known as trigonum spinae. So the connection is thorax trigonum spinae reaction force, and this area of the scapula is known as the angulus inferior. So thorax AI reaction force. Basically, they are reaction force of the connection between the scapula and the scapulothoracic guiding plane. Okay. And you have also other muscles like coracobrachialis. You have muscle biceps caput brevi. You can see the biceps caput brevi has one line of force. So it is not very distributed muscle. So the biceps caput brevi, it has one line of force, whereas muscle coracobrachialis has 6 lines of force. Okay. If I move on the other side of this scapula, on the posterior side, you can see more muscle attachment sites. Okay. You can, of course, see the reaction forces, the glenohumeral reaction forces on the right. You have the thorax TS, the trigonum spinae reaction force, and the thorax AI, because that is actually the scapula is being pressed on the thoracic cage. Now, from the back side, you have the major muscles which are responsible largely for movements. You can see muscle deltoides, 6 lines of force, all along the inferior side of the scapular spine. Okay, all along the inferior side of the scapular spine. And you have the muscle trapezius all along the superior side of the scapular spine. Okay, the spine is there. If I go back, I will just go back slightly to show you the spine. So this is the spine. So in the inferior side of the spine, there is the deltoides. On the superior side of the spine, all along the spine, there is the large muscle trapezius. 6 lines of force for trapezius, 6 lines of force for the deltoides. So on the fossa area, the thin laminated structure, if I go back, you can see here, this is the fossa area, the supraspinous fossa, and there's infraspinous fossa. So on this supraspinous fossa, the muscle which is attached is supraspinatus. So quite a large muscle attachment site, and we have 6 lines of force. On the lower side, which is even larger area of the attachment site, we have muscle infraspinatus. So supraspinatus attached to supraspinous fossa, infraspinatus attached to infraspinous fossa. Okay, almost nearly the whole fossa area. So this is from the back side. The front side of the fossa, you have the subscapularis, okay, which is also having 6 lines of force. More towards the border, the lateral border, which are more solid bony ridges. So in the glenoid, the lateral border, it's more solid bony ridges. I'll just go back to the structure. So you can see here. So these are solid bony ridges, okay? Not thin, so solid bony ridges on the back side also solid bony ridges. We have the muscle teres minor and muscle teres major. They are also having 6 lines of force. On the medial side, on the back side of the medial side, we have muscle rhomboides. This has 3 lines of force because its action is limited to a lesser area as compared to other muscles. So, and on the medial side of the fossa, we have muscle levator scapulae, which is also represented by 3 lines of force. So that covers almost all the muscles. Note a ligament, a very rigid ligament known as conodium, but we also call it conoid ligament. Okay? We will use later on when we explain the shoulder model of forces, then you will notice the contribution of the conoid ligament. Now, perhaps you have heard of the term rotator cuff muscles. Okay? The rotator cuff muscles is a group of tendons and muscles together in the shoulder, connecting the upper arm, the humerus, and the shoulder blade scapula. Okay? I have a real model of the shoulder. I can show you maybe after the presentation. But at this moment, you have to conceive from the presentation itself. So the muscles that constitute the rotator cuffs are the teres minor, infraspinatus, supraspinatus, and subscapularis. Okay, so these are the 4 muscles that together is called the rotator cuff group of muscle. Okay, so you have, I have already shown you earlier. So you have the supraspinatus, infraspinatus on the back side, and it is actually these muscles are covering the glenohumeral, mostly the glenohumeral joint, in such a way, and it is providing stability to the joint as well as providing motion in form of rotation. That's the reason it is called the rotator cuff. So what are the function of each muscle of the rotator cuff muscle? Each muscle of the rotator cuff inserts at the scapula and there's a tendon that attaches to the humerus. So they are muscles that are attached between scapula and humerus exclusively, no other bones. So these muscles provide rotational stability to the shoulder and allow the shoulder to rotate. Okay, so they are responsible for providing stability to the shoulder joint, because you can already see that the cavity of the glenoid, which is a socket, is not that deep. So it is a rather shallow cavity on which there is a hemispherical head of the humerus that rotates. So often many people have this disorder of shoulder dislocation. Perhaps you have heard about it, the shoulder dislocation or shoulder subluxation, where the humeral head actually dislocates in a particular direction while raising your arm, or particularly any sort of movement connected with your with the arm. So it suddenly dislocates, and this dislocation is primarily due to less stability in the joint. The stability, well, the rotator cuff provides that rotational stability to the joint. It also holds the joint in position, but there may be, defects, structural defects. Maybe it's too shallow. The joint is the glenoid cavity is too shallow, and due to certain rotation, the humeral head comes out of the socket. Okay, this is a very common problem in many subjects. Now, tears in the tendons of these muscles are called rotator cuff tears. The most commonly affected muscle is within this group of muscles. The most commonly affected rotator cuff tears happen in case of supraspinatus. Okay, so supraspinatus is on the back side, located on the back side of the scapula, and it is attached to the supraspinous fossa. So I have made a table for ease of understanding where you can see the origin and insertion of the muscles within the shoulder bone. So muscles trapezius, its origin starts from the thorax, but it is finally inserted. One part is inserted into the clavicle, the other part is inserted in the scapula. So it has 6 lines of force for the part which is attached to the clavicle, and 6 lines of force on the part which is attached to the scapula. So it has 2 parts. The muscle trapezius originating from the thorax, one is attached, inserted to the clavicle or the collarbone. So you know what is clavicle, I hope, everybody. So it's a long bone, and you can feel it in front of your, if you just touch it, it is very near to the neck. Okay, so the clavicle, it attaches to the clavicle, and one other part attaches to the scapula. And the number of lines of force, as I told you earlier, the number of lines of force increases in cases where there is large attachment sites, and it is more appropriate to represent the action of a muscle with no more number of lines of force, because the line of action would of course be different in case of large attachment sites. So this is a table that would of course it is prepared by myself, and it actually gives you a clear idea of the origin and insertion of the muscles, along with the number of lines of action or lines of forces that is used to represent these muscles. Similar to trapezius, you have deltoid muscle, which is a very important muscle that also has a clavicle part attachment, and that also has a scapular part. Okay, but here you can see this insertion, one clavicle humerus and scapular humerus. Okay, so these are mostly the muscles that are attached to the shoulder joint. Now, few slides I have borrowed from my earlier presentation long back. I could find it just for your better understanding. So it has a different background. So we have the joint degrees of freedom. So there are several joints, as you all know, and it is the most complex joint in the human body. But the benefit of these joints is that you get a large range of motion. So the joint has a large degree of freedom. As you all know, the number of degrees of freedom of a joint depends on the shape of the articular surface and the number of ligaments attached to this joint. Okay. However, for say a mathematical model, we generally neglect small translation and rotations. So this is shoulder joint is typically a ball and socket joint as represented in the slide itself. Okay, the other ball and socket joint is of course the hip joint. So we have the shoulder joint and the hip joint together, but what is the basic difference is that the hip joint has a deep hemispherical cavity within which the femoral head actually is seated very well. It's much more stable than the shoulder joint, which has a rather shallow socket in form of a glenoid cavity. So you can see it already in the picture. The shoulder bones, as I have told you, this is typically a view of the shoulder complex within the upper part of the skeleton. This is a posterior view. We are looking from the back. That's the reason the scapular spine is visible very clearly. Okay, so this is the left scapula, this is the right scapula, and as we are looking from the back side, the spine which originates from the fossa and curves towards the front, so that is visible here. Okay, and you can see very clear the collarbone, the clavicle, as I am pointing through the through my laser pointer. So clavicle, right clavicle, left clavicle. One end forms the acromioclavicular joint. The other end forms of the clavicle forms the sternoclavicular joint. That means it is connected to the sternum. Okay. So some few features, just would like to say that the shoulder complex is as an example of a closed chain mechanism formed by the connection of the thorax, clavicle, scapula, and the thorax. So we have this a closed chain mechanism. So because it's a closed chain mechanism, we have very restricted rotations. The rotations of the scapula on the thorax are pretty much restrained. And the muscle action around the sternoclavicular joint and the acromioclavicular joint are some sort of coupled. So the sternoclavicular muscle action around the sternoclavicular joint and the acromioclavicular joint are coupled. So simultaneous motion of the shoulder girdle. So you can see when I'm trying to raise the arm, there is simultaneous movements or motions of the different bones. And that movement between the shoulder girdle consists of all the bones that constitute the shoulder joints. So shoulder girdle and the humerus, they are called scapulohumeral rhythm. So there is a rhythm which means that there is simultaneous motion of the shoulder girdle and the humerus. Now, very important things that I would indicate in this slide one by one is we are moving towards finding out the degrees of freedom, trying to find out degrees of freedom of each joint, and then based on movements of the shoulder joints, we are going to quantify the total degrees of freedom in the joint. But before that, there are certain considerations that we need to explain you. So the shoulder consists of 4 bony elements. So we have thorax, clavicle, scapula, and humerus. Okay, so these are the 4 main bone elements. So we have thorax, clavicle, scapula, and humerus. The connection of the thorax, clavicle, scapula, and we can also add with a hyphen thorax again, is a closed chain mechanism. So due to this closed chain, the rotational and translational degrees of freedom of the scapula and clavicle are constrained. Okay, so you know, I hope you know what is meant by closed chain mechanism. That means it is fixed. So it is fixed to the rigid world. So we since it is a thorax, clavicle, scapula, again thorax, and basically the rotations of the clavicle and the scapula are somewhat constrained, meaning that not every orientation can be achieved. So it is not free to move in spatial coordinate system. The double connection of the scapula to the thorax. Now, this what does it mean by double connection? So one via the clavicle and the other via the scapulothoracic gliding plane. So the connection, there is double connection of the scapula to the thorax, one via the clavicle, one via the scapulothoracic gliding plane, results in this closed chain mechanism. The motion constraints are limiting the potential orientation. So this closed chain mechanism actually limits the potential orientations of the scapula in the spatial coordinate system. Now, we focus our attention to the joints. So we have three main joints, that is the sternoclavicular joint, acromioclavicular joint, and glenohumeral joint, each represented by spherical joints. So it has three rotational degrees of freedom straight away. Okay, so each joint has three rotational degrees of freedom because they are spherical joints. The scapulothoracic gliding plane is modeled with the thorax as an ellipsoid. So you will see later on, it is basically modeled with the thorax as an ellipsoid. Basically, there are 2 points, as I had indicated earlier. 1 point, 2 points on the medial border. One is, if you remember, I'll just go back to show you that slide. These are the 2 points: thorax TS connection and thorax AI connection. Thorax trigonum spinae represented by TX, thorax angulus inferior, that is represented by AI. Okay, so these are the 2 points on which it's better to look from the posterior side because the scapula is pressed on the thoracic cage. So the connection between the thorax and the scapula is through these 2 points, ideally represented. Okay, so let us go back. But it is, the scapula is sort of floating on the, it's pressed on the gliding plane, and we idealize that, model it as an ellipsoid. Thorax is an ellipsoid, which 2 points on the medial border are sliding. So hence, 2 degrees of freedom are constrained by the scapulothoracic gliding plane. So constraints, so these are rotations, free rotations, 3, 3, 3 free rotations. But at these 2 points, 2 degrees of freedom are constrained by the scapulothoracic gliding plane. The reaction force at this plane are perpendicular to the surface of the ellipsoid. And that reaction force is basically the thorax TS and thorax AI reaction force. They are perpendicular to the surface of the ellipsoid. And additional degrees of freedom, as I was telling you, is constrained by the assumption that the conoid ligament is rigid. So remember one thing, that the muscles always apply active forces, and the role of the ligament is to stabilize the joint. Okay, so the ligaments are actually applying reactive forces. Okay, so muscles basically apply active forces, and the ligaments are trying to stabilize the joint by applying constraining forces. So it is more constraints, and the conoid ligament is a rigid ligament, is assumed to be a more rigid ligament, and therefore it applies additional constraining degrees of freedom. If you move out of the shoulder complex, there is also the elbow joint in the upper limb. So the elbow joint is represented by 1 rotational degrees of freedom for the humeral-ulnar joint and another one for the ulnar radial joint. So 1 rotational degrees of freedom for HU joint, another rotational degrees of freedom for the ulnar radial joint. So with this conception, we summarize in form of numbers what are the degrees of freedom in the whole shoulder elbow complex. So degrees of freedom of the shoulder and elbow. See that the thorax with respect to the global coordinate system has 6 degrees of freedom. That means the thorax is free to translate and free to rotate. Okay, but that is the thorax. Now, if we consider the thorax to be fixed, then this part doesn't contribute in the whole degrees of freedom of the system. Or if we try to calculate the degrees of freedom of, say, the shoulder joint with respect to the thorax, then of course this 6 degrees of freedom will not come into play. Now let us move into the shoulder joint, where we have the SC joints 3, acromioclavicular joint 3, and the glenohumeral joint 3. So 3, 3, 3 makes 9. Okay. Now comes the constraining degrees of freedom. As we discussed, scapulothoracic gliding pain offers 2 constraining degrees of freedom. So we have -2. Conoid ligament -1. Okay, as discussed earlier. And as I told you, the humero-ulnar joint of the elbow, if we consider elbow, if we stop here in the shoulder joint itself, then this 9 minus 3 becomes 6 degrees of freedom is the degree of freedom of the shoulder joint with respect to the thorax. If we consider the full thoracic cage as well as the shoulder as well as the elbow, now as I told you, the HU joint has 1 rotational degrees of freedom. UR joint also has 1 rotational degrees of freedom. So we add 1, 1 each degrees of freedom to the elbow joint. Contribution of the elbow joint. If you consider wrist, it has 3 rotational degrees of freedom. More, it adds 3 rotational degrees of freedom to this whole complex. So if you consider thorax, shoulder, elbow up to wrist, the degrees of freedom is 17. Okay. Now, if you just consider the moments, so you have basically in the shoulder here, you have, forget about this this thorax now. So 3, 3, 3. So 9 degrees of freedom. Okay. So you have 9 degrees of freedom where you can have the moments, kinematic, and 8 degrees of freedom when we optimize the muscle forces. But together, it comes to 17. Now, the input motions in the shoulder complex are as follows. So 3 thorax rotations, 6 degrees, as I told you, 6 degrees of freedom for the thorax. So we have 3 rotations and 3 translations. Again, 3 degrees of freedom for the shoulder girdles, rotations of the AC and SC joints, 3 glenohumeral rotations, 1 elbow flexion extension, so that is a rotation, 1 pronation supination, that is another rotation. And you have 3 wrist rotations of the hand positions. Now, if I try to represent the action of the muscles and the joint reaction forces within the scapular humeral complex, it would look somewhat like this. So about 17 muscles are acting on the shoulder joint, and you can see how the muscle serratus anterior is trying to force the scapula to sit on the thoracic cage. Okay, so the muscle serratus anterior actually moves, is attached on the medial border of the scapula, and the action, as I was telling you, why we represented the action of the muscle serratus anterior in form of 6 lines of force. This is very clearly exhibited because you can see it cannot be adequately represented by 1 line of force, okay, because the action is quite convergent divergent type, okay. Similarly, you can see from the muscle trapezius, the pulling action of the muscle trapezius in the scapular spine. So it has each muscle line of force is representing a somewhat different directions distributed over the superior side of the scapular spine. So this is the other is muscle deltoides, the major muscle. As you can see, it is also attached to the inferior side of the scapular spine, and these are very approximate sort of a sketchy form of representation of the muscle action. Okay, and you have the glenohumeral joint reaction force, AC joint reaction force. If there was a clavicle, I could have represented the clavicle is not included in this. Okay? But muscle caput gravi, here also you see the muscle serratus anterior. So muscle serratus anterior is more from the front. Okay, anterior means in the front, and posterior is on the back side. If you want, you can refer to this. Is pretty old now, but it was one of the 2 pioneering papers of my supervisor. Just note, it's a single authored paper, long back in Journal of Biomechanics. Analysis of the kinematic and dynamic behavior of the shoulder mechanism. So back-to-back papers, you can see one ends at page number 550, the other starts at 551. Very famous, very pioneering study on the shoulder force analysis. So that's it. This is up to which I would like to discuss only a part of a big lecture, but this is up to which I would restrict my discussion on shoulder biomechanics. So the other part actually belongs to just a moment. Yeah, can you hear me, everybody? Can you see me?
Yes, sir.
Yeah.
Yes.
Yes, sir.
So up to this slide is the first part of the presentation, that is on the shoulder biomechanics. Okay. The other half is on shoulder replacement that I would not discuss now. Later on, when I discuss on stresses, strain in the bone inside the what is happening, how the load transfer is through the scapula, and all these things, shoulder replacements, failure, things like that. So that would come under shoulder replacement. Okay. So can I stop recording now?